I am Nathan Epstein. I'm a data scientist and web developer from New York. These are some places you can find me on the internet if you want to reach out and talk about anything that I'm going to talk about here. My talk is machine learning at scale. And so basically what that entails is going to be trying to understand some of the tools in the ecosystem for doing machine learning with big data, and then hopefully being able to get off the ground with applying some of those models to large data sets on a remote server cluster. So the ideal audience member is probably somebody that knows about, is aware of Spark, AWS, MLlib, and is sort of familiar with scikit-learn, but hasn't necessarily deployed sort of these big data tools in production. So, you know, if you're already working at a company where you are running large machine learning jobs on an AWS cluster, this is probably going to be pretty familiar. So the tools I'm going to talk about are AWS, Spark, MLlib, the Hadoop distributed file system, and optionally FlintRock. And I'll run through sort of talking about what each of these tools are. So AWS is a suite of cloud computing services that Amazon makes available on demand. And within AWS, there are a couple of tools that are sort of germane to our purposes here. So the first is EC2, which is rentable virtual computers that you can run pretty much whatever application on. Elastic MapReduce, which is a managed Hadoop framework to distribute and process data across a cluster of EC2 instances. S3, which is basically just very scalable and reliable cloud storage. And Spark, which is an open source cluster computing framework. So it's written in Java and Scala, but it's available for Python and R as well. And so in the context of this talk, we'll be talking about using it with Python. Then MLlib, which is a machine learning library built on top of Spark, again has APIs for Python, as well as several other languages. And while there are some subtle differences between the APIs for MLlib and scikit-learn, the basic structure of how they work and how to use them should be pretty familiar to anybody that already has experience working with scikit-learn. So the Hadoop distributed file system is a cluster file system, and so it's highly fault tolerant and also allows for high bandwidth for processing large data files quickly. And then the last tool in this stack, which again is optional, is FlintRock, which is a command line tool for managing Spark clusters on AWS. AWS also has a command line tool. It also has a web console if you prefer doing it that way. I mentioned FlintRock because I find it very easy to use, and but it's one of sort of many replaceable pieces for its part in the stack. So before I go to the next slide, I should mention I was without Wi-Fi for a part of putting this presentation together, and so there will be several very crude hand drawings as a piece. And with that, our first. So basically, just to make sure everybody's clear on sort of the stack that we're working with, we have from our local machine, FlintRock, which is used to manage an AWS cluster. And on that AWS cluster is the Hadoop distributed file system, Spark, which accesses that file system, MLlib, which is used to build machine learning models on top of Spark, and then your code, which uses these things to build specific applications. Okay, so crash course in Spark. There's the resilient distributed dataset, partitioning, and array methods. So the RDD is sort of the central data structure in Spark. And basically what it is it allows for common array type methods to be performed over a data set which is distributed over a cluster of machines. So basically it will take your data set, distribute this over the cluster that you are using, and allow you to perform common operations in a way such that the parallelism is abstracted away from you. So partitioning, which is basically how we read in a data set and partition it across a server cluster. So we can either parallelize a list that we have locally, as in that first example, in which case Spark will create an RDD, or another RDD in which we could read in from a text file, in which case each line of the file is processed as an element of that RDD. And then we can recollect the elements that are distributed across the cluster of nodes by calling collect, and that will return a list. Generally, it's considered pretty dangerous to do this unless you're sort of very clear about you having reduced an RDD to a size that's manageable, because the whole point of using RDDs and distributed computing in general is that having all of your data on a single node is too much. And so you can wind up getting into trouble as a warning. Drawing number 2. So this is basically just a very crude visualization of the parallelization that happens. We say if I've got a 3-node cluster, then I call parallelize on my list, and it'll break up this list into a bunch of smaller lists and send a piece to different nodes in the cluster so that we have smaller, more manageable data sets on each of these nodes. Obviously, this example is kind of silly because a 5-element list is totally manageable on a single node, but you can imagine if this list was much longer, then breaking it up into these pieces would be important to do. Okay, so array methods. These are methods that are hopefully familiar, and I have array in big quotes because we're not actually operating on an array, but the RDD allows us to abstract that fact away and basically treat it as if it's a single data structure in a single location and not have to worry about the fact that all of our values are distributed across a lot of nodes. So in the first case, array map, it's very similar to the syntax of Python map operations on lists, but rather than passing in a list, you're calling it as a method of the RDD, and then you simply pass the lambda to that method. So in this example, where we say our lambda is just going to be x times 2, our RDD is distributed across the 3 nodes, and on each individual node we do the mapping so that in the RDD that this returns, we have values 2 and 4 on one node, 6 on another, 8 and 10 on another node. And again, because we're doing this mapping in parallel, each node has less work to do, and so we can do it faster. And then if we were to call collect on that RDD, it would return the list that you see at the bottom of that. Reduce, fairly similar. So we have our RDD distributed across our 3 nodes. We call pass it a lambda with our function, which is just going to be add 2 values together. And then it performs the reduce function on each of the individual nodes to get the values 3, 3, and 9, and then a reduce again across the output values of those nodes to get a final value of 15, which would be the sum of the list that we're looking at. And filter, I think the idea is pretty clear at this point, but so the lambda we're passing is just to check if a value is even. We filter the individual lists on each node, and then the filtered RDD at the end, if we collect it, is just 2 for the even values from the 2 separate RDDs that have even values. Chaining works basically the way you would expect based on that. So you can call a chain of these methods on an individual RDD. So filter for the even numbers, then map them to double, and then reduce them by adding would give you 12, which is the doubling of 2 and 4, the only positive values, and then some. Even values. Okay, so that's it for the drawing portion. And on to MLlib. So like scikit-learn, MLlib supports a lot of common machine learning algorithms and supervised and unsupervised learning. And the advantage of the library is that it creates very straightforward APIs for training and making predictions from data sets. So you have individual models which train on data which is formatted in a particular way, and then you can call predict on like new values which are formatted in the same way as your input data. Does a lot of other stuff too, like common summary statistics, hypothesis testing, a bunch of other stuff. Way more stuff than we have time to cover. But I think sort of the bread and butter functionality is in this like application of common supervised and unsupervised learning algorithms. So just to get a little bit of a flair of the syntax, here's a linear regression example. So you could create an RDD by reading in a text file with rows of some data, and then parse that data by mapping to another RDD. The parsing function being something that we specify not on this page because it's generally going to be specific to the type of model that you're using. And then in building the model, we pass our parsed data and then some parameters about how the model should be trained to our linear regression with SGD, which would be stochastic gradient descent. And so you just need to pass that data and specify some parameters that are specific to the model type. And then prediction works basically the same thing as the same way as how scikit-learn would work, where you just call .predict on your model and pass it a point to consider. Fairly similarly, unsupervised learning. So k-means creating clusters of related points within a data set. Read in some data, train, pass model parameters, so the number of clusters, the number of iterations, how we initialize the centroids, and then we can print predictions just by calling predict on the model that we've trained. That basically covers the like surface level introduction to all the different moving pieces within this stack. And so I thought we could run through basically like an example problem, which would be like taking classification, but with a really large data set. And so we'll build a program which will do the classification using PySpark and MLlib and talk about how we deploy that to an AWS cluster. So for our example, we'll say that we have a data file that looks roughly like this. So the first element of each row will be a character that we're trying to recognize, and then all the other columns will be features. The details of what those features are don't particularly matter. They're features, they're numeric. Code to analyze this, and it's split over a couple slides. So in the beginning of our code, we'll import the dependencies. So random forest will be the model type that we'll use to do the classification. We'll also import labeled point, which is a way of parsing the data in a way that MLlib is and random forest is happy with. And then we'll import Spark context, which will allow us to create the RDDs. And then at the beginning, we're basically initializing our Spark context and creating some convenience variable and function in order to map our letters in each row to an integer value. So splitting up the data into training and validation and actually training our model. Our raw data will read in a text file from the file path specified, which notably is on the Hadoop distributed file system. We talked a bit earlier about the fact that this is where Spark will be pulling our data from, because the file needs to be held in such a way that we can read it and distribute it over the cluster. And we'll circle back to how we actually get it onto the Hadoop distributed file system in a bit. We'll make our labeled points by using the clean valued function that we defined on the last page. And then Spark has a pretty nifty convenience method for doing a random split on the RDD. So across all of these nodes, we're choosing a ratio of 70 to 30 of the values on each node of the cluster to partition either to the training set or the test set. So that way we start with a sample of 30% of our data set, which is there for validation after we've trained on the bulk of our data. And then the model, we will train a random forest classifier on the training data and specify some parameters about how that model is trained. So first, the number of classes, there are 26 characters in the English alphabet. Any metadata about the categorical features, max depth. There are 16 features, and so you'd only want the tree to be able to go 16, perhaps. There obviously aren't definite values for any of your parameters. Any model has your training, you're going to do parameter tuning. This is just what happened to work well in this case. And then scoring an output for our model. So we map, we get an RDD of labels, which will be like the actual values of our test data. And then we get predictions on those same points by calling model.predict on each of the test sets features. So basically, we're creating RDDs with both the actual values and the values that our model predicted in order to get a sense of how well our model performs in predicting those actual values. And so labels and predictions, we're zipping predictions into labels, which is basically just to create an RDD of tuples so that we have a tuple with both the actual value and the predicted value for comparison. At this point, we're going to filter out only the values that match between prediction and actual output in order to get our total correct. And then the percentage that we actually get correct will be the number of those that were correct divided by the total number of points that we're looking at. So at this point, our program is just going to finish by printing out that percentage of correct values for our model. And I sort of have this comment here to sort of loudly state that, like, this is obviously a sort of toy example, in that, like, if you're doing machine learning in practice, you obviously don't want to just like stop by knowing how well your model does. You'd probably want to know, be able to use that model. So at this point, like, you might either want to write that model to an S3 bucket, possibly, for example, so that you can use it in the future to actually make predictions in some sort of application after the end of this program. That's the code that we're going to run and the data that we're going to use. One of the barriers to actually doing this kind of work is that getting all the pieces of this stack set up and working together and playing nice together is not always trivial to do. And so I wanted to sort of finish by running through sort of the pieces of the stack and how we can actually get them to work together, so that we see like the whole sort of process of running your application. And so, yeah, that will entail setting up Flint Rock, launching our cluster, setting up the cluster, getting our files there, getting them into the Hadoop distributed file system, and then finally running the code on that cluster. So for setting up Flintrock, again, this part is entirely optional. There are plenty of other tools that serve this function in the stack. There's a GitHub repo for it, which has good instructions for installation. And then if you configure, it'll provide you with a YAML file that will basically ask for information about your AWS credentials so that you can use that to seamlessly launch your clusters and not have to deal with all of the AWS stuff every time you want to launch a new cluster. And then the commands for actually launching your cluster, once that's done, are pretty straightforward. You just launch a cluster, and it'll use your configuration file in order to decide like how many nodes, how big are your nodes, and launch that. And then by doing Flintrock login to your cluster, you'll be taken to a command line interface for the master node of the cluster. The next thing we have to do, if we're going to be using MLlib, MLlib has NumPy as a dependency, and so we'll need our machines to actually be able to use NumPy. And so we'll install a C compiler so that NumPy can be installed, and then install NumPy. Getting files to the cluster. This is a context in which using S3 makes a lot of sense, because the whole point of our problem is that we're dealing with very large data. And so having to upload locally to the server cluster is not something that's going to be particularly easy to do. And so it would be better to copy our data from an S3 bucket. And so your AWS EC2 instances will come pre-installed with the AWS CLI. And so you can use that to copy from a bucket to the local path on your cluster. And so in this case, I have a bucket called Python Epstein, in which I have data, the data that we looked at before, as well as the code that we ran through. And so I could use this CLI to just copy those to the local file system on the cluster. And then, in order to actually be able to read those in a Spark program, they need to be accessible on the Hadoop distributed file system. So rather than just being able to read them from the file system on the master node, we put them on the Hadoop distributed file system using that syntax, which is just fsput, the path to your local file, and then the path that you want to store them at on the HDFS, which in this case is just in the root directory. And after that, it's just running your code from the HDFS, and that's the whole process. Yeah, that's it.
Thank you, Nathan. Questions? We have quite a bit of time for questions, so don't be shy. Question over there? Wait.
Thank you. Thank you for the talk. Sorry. How is it to run programs that rely on CUDA on the clusters? If it's
not really sure. Yeah, I can't say from personal experience. Yeah, sorry.
Okay, thank you.
Other questions?
Hi. This might be too generic and vague, sorry about that. But how do I know how many cores to rent at AWS?
Yeah, I mean, obviously, that's just going to be a question of like application details. So I guess I could talk just a bit about like the trade-offs you'd want to make there. Yes. So the first obvious concern is like how large is your data set? The larger your data set, the more cores or size of cores you would want. I guess it also kind of depends on based on like the actual contents of the application, you might be fine with running like over a slightly longer period of time. If it's like not something that you need to process immediately, if it's like a cron job, for example, then you could either, yeah, if it's like something that you don't need immediate feedback on, then you can use a smaller number of cores. But yeah, it's hard to say without more like specific details.
One more question over there.
Thank you also for that talk. My question was, you mentioned repeatedly through your talk that, of course, we have really big data. And in the pipeline that you showed, you just copied the data from the bucket to your local home on the cluster, and then from there into the HDFS distributed thing. Wouldn't it be better to just pull it from the bucket into the HDFS without the intermediate step?
Yeah, so uploading to the HDFS is kind of misleading. So the idea is basically that like it's abstracting a file system away from you. Really, it's just like reading the file in a way that is partitioned, but the data doesn't move again at that point. So when the only like actual transfer of data is from the S3 bucket to the cluster, and that's going to be faster to do than from locally, because that's all like internally on like Amazon's cloud storage. But like when you're copying to the HDFS, it's kind of an abstraction that it's a file system. It's not actually moving again.